Thank you all for coming. We have an amazing response here today. You know, like in the history of doing JavaScriptLA, I've never seen so many people RSVP and come for an event, but obviously Douglas Crockford, so that's really cool. Thank you so much to Mr. Crockford for coming out and wanting to do your presentation with our group. I am the organizer, VJ. Some of you know me from Slack. That's how we communicate through JavaScriptLA. We have about 730 engineers on that, and we've been doing meetups for a while. We are doing something brand new today. We are live streaming this event, so people at home can also watch this event, which is pretty cool. This is kind of the first time we're doing that. So we ask that, I know this is kind of a drag, but if you're not using your Wi-Fi, please go ahead and just turn it off, or like keep it, because we're streaming through Wi-Fi. You can keep it on LTE or cellular network. That's totally fine. We just want to clear that so we can do this without too many hiccups. Okay. Can I get a show of hands here, just real quick? How many people heard about this meetup through Eventbrite? Okay. And how many heard through Meetup.com? Okay, overwhelming. Yeah, that's pretty typical. Okay, so a couple thanks before I do anything else. Number one, thanks to Codesmith, thanks to Santa Barbara JavaScript, Code District, and then Azad Mardan, and I think there's a couple others that I'm going to read to you that I need to thank for putting this together. It's a lot of work actually to put this meetup group together. So if you can support us by subscribing on YouTube or Facebook, all the different channels that we have, and just really help us grow, that is like the biggest thank you we can get. And also, of course, engaging with the group on Slack, just asking for more presenters, more things you want to see in the group. I'm the person you want to talk to most of the time, like about events and stuff. Daniel's our producer. Sean is also in the audience here. He's a cool guy. One more thing here, I guess you have a bunch of ASTQB's flyers. These are brochures. These brochures have been given out to us. It is essentially, they want to thank JavaScriptLA for having the opportunity to sponsor this meeting. I'm going to read it right here. As the representative of ISTQB software tester certification in the US, ASTQB is pleased to support the development of quality software in the United States. Local groups such as yours are vital to that mission. With more than 300,000 ISTQB certified software testers globally, ISTQB software testing provides a professional pathway for professionals such as you. Not only is it practical, but given that ISTQB certification is offered in nearly 70 countries globally, it serves as an international standard that makes both you and your company global ready. So a special hello to ISTQB certified testers in attendance. Have a wonderful meeting. So that's, again, if this is something of interest to you, if you're looking to take your software engineering to a different level, you can check this out. We also want to thank O'Reilly for putting all these books together. This will be part of our raffle tonight. So some of you might get some books. Did anybody bring a copy of JavaScript: The Good Parts? Okay, you did. So Douglas is saying that he might do at the end, maybe along with the question answers, signs, autographs and stuff. So very cool. Okay, that's all I have. Does anybody have any questions for me before I hand it over to Douglas? Okay, cool. Thank you so much for coming, and I'll be here at the back. Well, actually, I'll be right here, but at the end of the meetup, I'll be around for questions if you have questions for me. But enjoy the presentation, and let's give Mr. Crockford a hand. Thank you so much.
It really is great to be back. I used to live about a mile from here, just on the other side of the freeway. There used to be a computer industry in Orange County that actually built hardware, built mini computers. It's all gone now, I guess, but you're still here, so it's really great to see all of you. Thank you, everybody, for helping to set this up and to provide us this place, and thank all of you so much for coming out tonight. So I want to do for you tonight a brand new talk. I have never done this one before. I think it's a really important topic. It's a really interesting topic. It turns out the way our character codes work has a tremendous impact on how we think about programming and how this whole profession operates. A lot of stuff is implied by the way we handle characters. Computers are machines that manipulate numbers. That's all computers can do. That's literally all they can do. But by assigning numbers to characters, we can do text processing, and all this information stuff happens. And I'm going to talk about where this stuff came from. I think this is going to be an interesting talk. It's certainly interesting to me. I love this stuff. And we're going to be talking a lot about the history of this stuff. But I have not been able to figure out how to end this talk. And I've done this before. I've gone out and I've had a talk, and I really like this talk, and I go out and I don't know how to end it. So I just go to the end and say, thank you, good night. Knowing that it deserved a wow finish, but I didn't give it one. Because during the UA, or in the QA, I'll get questions. And some of the questions will indicate that I completely failed in trying to describe what this is, because the question just completely missed it. But sometimes the question will focus me on what the whole thing was about and go, yes, thank you. This is the moral of this story. So I'm hoping that'll happen tonight. So I'm counting on you. OK? You have a part to play. So character codes don't start with computer systems. They start first with data communications, or communications in general, just human communication, and then data processing, and eventually communication and data processing come together in computing. So we're going to start at the very beginning, the first character set, the Morse Code, designed by Samuel Morse, an American portrait painter. He also had a hobby in electricity, and he worked with some partners to develop a telegraph, and Morse put together the code that transmitted words across their telegraph. And it's a very, very simple code, because their telegraph, all it could do was transmit two states. It was either on or it was off. So Morse figured out a way to turn that into a communication channel. So he has a language that's made up of two symbols, dot and dash. And we can represent these in binary. So a dot is a single one, and a dash is 3 ones. And then in order to tell the difference between the dots and the dashes, you need to put some zeros in between them. So he's got 0 for the particle space. That's the small separator between a 0 and 1. And then there's a letter space, which will be the space between the letters, and then a word space, which goes between the words. If you're a musician, it's easier to think about this musically. So you can think of a dot as an 8th note, and a dash is a dotted quarter note. And then an 8th rest is the particle space. A dotted quarter rest is a letter space, and approximately a whole rest is the word space. So here's an example of 4 letters represented in the Morse code. So the letter T is a dash, letter I is 2 dots, letter M is 2 dashes, and an E is a dot. So Morse took a look at the frequency of letters in English and chose the most popular letters to have the shortest codes. So this is not only a communication code, it's also a data compression code. It's the first data compression code. And it's a code that works in time. Most of our codes work in space. You can think of a word containing some number of bits, or even a packet containing some number of bits. But this is because it's musical, it's all happening in time. So remembering the word time will help you to remember these symbols, that the consonants are dashes, the vowels are dots, and the most frequent things, like the E, will get the shortest code. Okay, so you now know 4 of the letters in the Morse code. In fact, I'm going to teach you all 26 letters of the Morse code because you might need it someday. You might be trapped in a mine or on a disabled submarine, and you're going to need to be able to get a message out. And all you're going to be able to do is tap on the hull with a rock or something. But you'll be able to do it because you're going to know the Morse code. OK, the fifth symbol is the V, which we can get from the V for victory, Beethoven's Fifth. So you all remember Beethoven's Fifth Symphony begins dot, 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 dash. OK, that's the letter V. OK, V for 5. You all know the SOS, the International Distress Signal. It's dot, 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 dash, 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 dot, dot, dot. If we break it down into letters, the S is 3 dots, and the O is 3 dashes. This is the opposite of the dashes being consonants, but you know, we've got a couple exceptions, so you can remember that, right? So dot, dot, dot is S, dash, dash, dash is O. H is a little tricky to remember. It's 4 dots. So I recommend you think of the 4-H Club. And the advisor to the 4-H Club, Mr. 4-H himself, Harry Herbert Hoover Heaver. OK, for the rest of the letters, OK, so you now know 6 letters, right? For the next 20, we're going to have some mnemonics. And this is how the mnemonics are going to work. So I'll give you a letter, and I'll show you the Morse code for that letter. And then I'll have an English word which contains that letter, in which the dot corresponds to a vowel and the dash corresponds to a consonant. So A is for am. Everybody got that? Am everybody understanding A? OK. Let's move on. B is for bow. Be my bow. It's beautiful, isn't it not, my friend? C is for cocoa. Everybody loves cocoa, right? You love cocoa. That's why you can remember that C is for cocoa. This next one is going to be really shocking and upsetting. D is for die. But because it's so shocking, you're going to remember this one. D is for die. E, you've already seen. E is one of the time things. It's 1 dot. And F is for oofy. That's right, oofy. Everybody say oofy. Oofy. OK, so ambo, cocoa, die, E, oofy. Everybody with me so far? We're learning the Morse code. G is for GNU. For programmers, that should be a really easy one. I mean, G, GNU. G, GNU is that outfit that gave us a failed Unix clone and a software license in which free is not free, right? Everybody knows that one. We've already seen H, the 4-H Club, Harry Herbert Hoover Heaver. I, we've already seen I, right? 2 dots in I. J. Hey, J, what do you say? I, JJJ. You what? I, JJJ. K is for kit, right? That's easy. Kit, K, kit. Maybe K. And L is for soothing, aloe. You can't forget that. L for aloe, of course. So GNU, 4-H, I, JJJ, kit, and aloe. Everybody still with me? Let's learn some more. M, we already saw, is one of the time letters. And it's good. Good. The letter M is good. N-O, no. Got it? OK. We already saw O from the SOS. P is for expo. You might imagine next year there's going to be a big expo in which they're going to announce a better mnemonic for the letter P. So we're all looking forward to that. Q is a bit tricky because it's hard to make words out of Q. So whenever you have a Q, you're likely to have a U after it. So we got that pair. And we're going to wrap it in quotes, but we don't have quotes. So we'll use the letter Q for the quotes because Q is for quote. And so we get Q, Q, U, Q. OK? Got it? R is for era. This is the era of Morse code, R. Yeah. OK. S, we already saw in the SOS, in the distress signal. We already saw T in the time letters. U, out. O-U-T, out. OK. We already saw V, Beethoven's Fifth. Da, 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 da. W is for the wise old owl. That's easy to remember, W and the owl, because he's so wise. X is another hard one, but fortunately X rarely happens in English, so we're safe. But you know, it's XOOX. You're not going to remember that, but you'll probably be OK. Then Y, yuck. So you know, if there are any little kids here, I don't see any little kids. If there were any little kids, the two symbols they're going to remember tonight are oofy and yuck. That's for sure. And then finally, at the end of everything is Z, of course. So what comes after zoo? Zizoo, right? That's the end, right? Zizoo is the last. So you now know Morse code. You're not good enough to get an operator's license. But you could probably recall this and make a list, and then you can tap it out. You know, you might be on that disabled spaceship, and you need to alert the fleet. You're going to be able to do it. Someone's going to say, my God, that's Morse code. You know, it will be saved. OK, so moving on. The next communications code was the Baudot code, which was invented by Émile Baudot, who was a French telegrapher. He wanted to improve on the telegraph. So instead of the operators having to be entering a stream of bits, that instead you would have a keyboard that would look like a musical keyboard with 5 keys on it, and you would chord in the letters that you want. So you would have to memorize the letters in order to get them in. And this keyboard would be attached to a paper tape punch, which would produce a string of paper tape with the holes in it, and then that could be transmitted. There was another guy who came, and so have you ever heard of baud rates? Which is, yeah, a couple of the old timers going, yeah, I remember baud rates. Baud is usually bit, yeah, well, it actually means bits per second, but yeah, slow is also another meaning. So it was named after this guy. So Donald Murray, who was a New Zealander, improved on Baudot's system. He came up with a much better keyboard, so it had a button for each of the letters, and so the operator didn't have to memorize the binary codes. He'd just go punch, 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 punch. And he could have picked any keyboard. And unfortunately, he picked the QWERTY typewriter keyboard. The QWERTY typewriter keyboard is terrible by design in order to try to prevent the jamming of the mechanical keys. And it wasn't completely successful in doing that. But that's why it's got that bizarre layout. And Murray could have said, well, we don't need to do that because, you know, when you push a button, we're closing a circuit, which is going to drive some pins through some paper tape. So it doesn't matter what order we put the keys in. He could have done something rational. But he didn't. And so we're still stuck with the QWERTY keyboard everywhere. This is the first time QWERTY is used in electronic communication. And it's still being used in electronic communication. So this is a refinement of the code that those two guys worked on. And it became a standard, one of the first telegraphy standards. This is International Telegraph Alphabet number 2. It was a 5-bit code, which allows them to encode all of the letters. Murray scrambled the codes around in order to reduce wear on the machinery, so that instead of optimizing for time, he was optimizing for bits, where each bit would cause a needle to drive a hole into a piece of paper, and those pins would wear out. And so in order to reduce wear on the machinery, he had the most common codes have the smallest number of bits. So for example, E is a very popular letter. It only has 1 bit. And T is also a very popular letter. It only has 1 bit. And since the operators didn't see the codes, it didn't matter that they were kind of random. Then there's a code for space, carriage return, and line feed. 2 separate codes because that's how his printer worked. The most interesting thing that Baudot did was he added a couple of shift keys. So there's the figure shift and the letter shift. So when you're in letter mode, you get these codes. And when you're in figure mode, you get these codes. So that gets you the digits and the special characters, which was a really clever idea. So they managed to get 60 or so characters in just 5 bits. And they decided to have 2 codes instead of 1. They could have just had a toggle shift. But there was a concern that the telegraph lines were very noisy. And if there was a line hit, then a shift code could get garbled. And that means everything after that is going to look wildly wrong. So to make the system a little bit more resilient, they have 2 independent shift codes. So the next step happens a bit later, the Hollerith code. So Herman Hollerith developed a data processing system using punch cards for the 1890 census. The US Constitution requires that every 10 years we have a count of everybody, so we can figure out how to staff the House of Representatives. And it was taking too long to do with pen and paper. So Hollerith figured out a way to do a lot of that work mechanically. And that turned out to be a big business. A number of companies were formed. And after a series of acquisitions and mergers, Hollerith's company eventually becomes International Business Machines, or IBM. And in 1928, IBM wanted to figure out a way to get more information onto the cards. Because with Hollerith's little circular punches, they could only get so many characters, and they wanted to get more. So they came up with a system in which they could get 80 columns on a card. Each card had 80 columns and 12 rows in which you could punch holes. And at the top, there was a blank space where you could print stuff with ink so that humans looking at the card could figure out what it said. Although people who were skilled with this code could actually look at the punches and tell you what it said. So they came up with a very straightforward way of encoding the characters. So first, if in the top line, it's called the 12 row or the 12 punch or the X punch or the plus. So if there's a punch there, then you get a plus sign. The next row, you get a minus sign, and then 0, 1, 2, 3, 4, and so on to 9. Okay, pretty straightforward. And they wanted to be able to do letters, too. So letters are slightly more complicated. Each letter requires 2 punches because we've used up all the 1-punch codes. So we use the plus row and the digits 1 through 9. And that gets us the letters A through I. And then we do a similar thing with the minus row and the digits 1 through 9. That gets us J through R. And we do a similar thing with the 0 row, but this time going 2 to 9 to get S through Z. This pattern should give you 27 letters, but we only need 26. So they needed to drop one of the codes, and the code they decided to drop was 0, 1. And the reason was that you had 2 holes with just a tiny little piece of paper between them. And there was a concern that given the crude machines of the time, that they were using metal wire brushes to sense the holes in the cards, that it could rip the card, which could cause the machine to jam or cause bits of little pieces of paper to accumulate in the machine and eventually catch fire. So to avoid that hazard, they skipped that code. Then you could have 3-letter codes or different combinations of 2-hole codes to do the special characters. And unfortunately, that never got standardized very well. So different machines would have different codes. So taking a deck of cards and moving it from one system to another could get really complicated because all the special characters could get misinterpreted. So now we finally move into computing. When computing starts in the late 40s, the first computers have 6-bit character sets. These machines were mostly concerned with computation, mathematical computation, and so 6-bit character sets were fine. So this is one that was used at IBM. Their character set was based on a printer that they were using with their punch card equipment, which they modified in order to work with some of their early computers. And so their printer only could print 48 different characters, and so they left a lot of these codes blank. And they had a few weird characters like that. What is that? I don't know what it is. It's called a square lozenge. I don't know what it means, but it was on their punch card equipment, and so people would use it because there weren't very many characters available, so that meant whatever you really wanted it to be, you would use that because that's all it is. They didn't put a plus sign in it, which is like, I don't understand. So the next step forward is Fortran. Fortran is the first really successful programming language. Kind of changes the world. It was also developed at IBM, and it gets ported to all of the IBM machines, and then everybody else makes their own Fortran systems as well. It's the first big programming language. And the guys who were designing Fortran couldn't figure out a way to make a programming language out of that. So they said, we need these additional characters. And so they just said, if you're going to have Fortran, you're going to have to get these characters somehow. And so IBM said, well, OK, we'll try to figure out how in our next printer we can add those. So in a later version of their BCD-C code, they've added more characters. So something that's weird about this, you look at the arrangements of A, J, S. What they did was they just took the Hollerith code and pushed it into the character set. Okay? So we have an expectation that each letter is going to be one away from the next one, but that's not the case here. I plus 1 is question mark, not J. Okay, so it's going to be a little challenging, write a sort routine for this character set. Okay, and they got some weird characters like these guys. So they created a magnetic tape system to work with this computer. And they reserved these 4 codes as special marks on the tape. And they recommended that you never use these codes in your programs, because if you try to write those codes to the tape, it's going to screw everything up. So they picked characters that they thought no one would ever want to use. Then they had a problem. They started selling stuff in Europe and found that this isn't enough letters. That like in Scandinavia, they need 3 more letters. And so they decided, well, you can take those letters or those characters and replace them with letters in whatever country you're in. So this kind of begins the I18N problem. This is where it starts, and it took a long, long time to fix it. Now, it turned out every company had their own character set. So for example, Control Data started with the IBM set, but kind of changed a little bit because they were more into scientific computing, and so they added some characters that they thought people who were programming about numbers would care about. Things like not equal, less than or greater than, angle brackets, or less than or greater than. That's good stuff, right? Another company that was doing brilliant work, the Burroughs 5000 series, is maybe one of the most interesting architectures ever designed. And they're still doing the IBM thing, except they kind of straightened it out a little bit. At least A comes before S now, so that's good. And I really like that they put zeros at the top row. That means the character code for 0 is 0. Does that make sense? That absolutely makes sense. That's brilliant. As a programmer, I love burrows. That makes so much sense to me. And a pretty good, nice set. Oh, and they got an arrow, which is what we should have had for the assignment operator. Fortran didn't have this because they just didn't dare to ask for another character. And so they were forced to use the equal sign for assignment because they had no other options. And we're still doing it. It just doesn't make any sense. We should be using that. Or that makes sense. So the US Army is buying lots of computers, and each of its computers comes from a different company, and they all have different character sets, and trying to exchange information between all these machines was really, really hard. So they decided to fix the problem, being the government. So they created a character set of their own called field data. And field data was a 7-bit character set, which was intended to run on all Army computers, and that would let them communicate. But because it was and there's some pretty reasonable stuff. So they finally fixed the alphabet, right? So it's all continuous. So I like that a lot. And it's still got some of these weird IBM characters in it, but that's OK. And some of these could be replaced by other characters. And for some reason, they moved all of these characters up to the top half of the 7-bit character set. And they left the bottom half of the 7-bit character set undefined. So there were a number of projects in the Army that started working with this character set, and they liked it, and it worked well. And they had need for lots of extra characters, and there was all this 64 characters that weren't being used, so they just started using them, which was fine for them until the Army wanted to make all of these programs work together, and they didn't, because everybody, so there was a hard lesson there that you really have to nail stuff down in a standard. If you leave too much stuff free, then programmers will abuse it, and as a result, you'll lose interoperability or quality or whatever it is you're trying to get. So the next big step forward is ASCII. Anyone heard of ASCII? Yeah, ASCII is a big deal. The American Standard Code for Information Interchange. Work started in 1963. And ASCII was a joint project between AT&T and IBM and a whole bunch of other parties. It was not intended to be a computer character set. It was intended to be a network character set, or a communication character set, but we'll not only have teletypes on the line, but we'll also have computers on the line using the same code. So this is a big step forward. Initially, ASCII was going to be a 6-bit character code. Basically, they're going to take the Baudot idea, but add one more bit to double its capacity. And they wanted to be able to represent uppercase and lowercase. And the way they were going to do it, which I think was completely reasonable, was they were going to borrow the shift idea that was in the Baudot code. So they would have shift uppercase and shift lowercase. And that would have been brilliant, because the way we would deal with case today would be exactly the way we deal with color or underline or italics or anything else, small caps. It'd just be, you have a code which represents a letter, and we'll have some other means of saying what glyph we want for that letter. But they didn't do that. And the reason they didn't do that was, again, the line noise problem in the telegraph lines. That the lines were really noisy. We didn't have the error correcting codes that we have now. Our error correction systems are so good, we're not even aware of them anymore. But when this was designed, line errors were a really big problem. And their concern was that if one of these shift characters gets mangled in transmission, then the rest of the document is going to look stupid when it's printed out. And to deal with that, they decided, let's change it into a 7-bit character set and give each of the letters a separate code, which I think was a terrible decision. The reason they did that stopped being necessary a long, long time ago, but we are still stuck with the consequences. So this is the code that they came up with. 32 transmission control codes at the top. Anybody have any idea what those are? You might recognize one or two of them. Most of them are a complete mystery to you, but they're still in the code. Then we've got the digits are lined out pretty nicely. It's actually a pretty nice thing. They considered interleaving the upper and lowercase characters. So you'd have uppercase A and lowercase a, uppercase B, lowercase b, so that most things would kind of sort right. But they decided it doesn't sort perfectly. And rather than try to figure out how you might fix that, the way you might fix it would be to go back to the 6-bit code. They decided, let's make it really wrong. And we'll separate them by 32. So, so you're probably curious about what those control codes are. Tonight, for the first time, I'm going to tell you what those control codes mean. So AT&T insisted on two codes, null and del, delete. So these were for punch paper tape applications. So on the punch paper tape, 0 means there's nothing punched on the tape. And 1 means there is a punch on the tape. So they wanted blank tape to have a code that you could recognize and reject. So you'd have a liter of blank tape, and you'd run that through your tape reader, and you'd send it to the other side, and the other side would see, oh, that's just a 0, I'm going to ignore it. Which sounds bizarre in our modern system. The internet doesn't work that way, but that's the world that this code was designed for. And then, so offline, you're editing a paper tape, and you make a mistake, and you go, oops. So what you do is you back up the tape and hit the delete button, which goes chunk and punches out all of the holes. And then you can punch the character after it. So punching out all the holes means this is a non-character. Ignore this non-character. So it means the same thing as null, but it just happens to have a different code because that's how paper tape works. So then there was also a backspace code, the BS code, but it did not mean erase the previous character. It was not designed for user experience. Because there were no users, there was no experience. This was just designed for machines talking to each other. So backspace meant move the print head back 1 space, which that's a completely different meaning. Later, programmers said, oh, look, there's a backspace key. Oh, there's a delete key. Let's figure out what to do with those. And the things we do with those now are completely different than what they were intended to be. We're in complete violation of the ASCII code in the way we use backspace and delete. There were some codes added for operators, for teletype operators. There was the inquire code, which when you sent it to another terminal, would cause that terminal to send back a string which would identify the terminal so you know who you're connected to, which sounds bizarre today. How could you connect to something without an expectation of who you're talking to? And then there's the bell code, which will ring the bell. So you go Control-G, and on the other terminal, it'll go ding. So you go ding, 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 ding. Wake up, ding, ding. There was space and there was tab. Space was necessary because you need the interword gap. Tab was borrowed from manual typewriters. Manual typewriters had a tab key. You press it, and it would release the carriage until it was stopped by the next mechanical tab stop. Unfortunately, they didn't indicate any way of specifying how to set a tab stop. And they didn't specify what the default tab stops are. They just said, if you're going to tab, this is the code. And they never anticipated what we're doing with this stuff. And unfortunately, this is a source of conflict. We're still arguing. Should we use tabs? Should we use spaces? It's a colossal waste of time. And the debate goes on and will never stop because there is not a clear answer. Neither side can prove that they're more right than the other side. And lacking any way of resolving the conflict, it just goes on. And the cost continues to grow and grow and grow. The value of having these two characters, 0. We get no value from having two ways of doing this thing, or at least compared to the cost that it causes. So I recommend a different way of resolving this problem. Which one can we get rid of? We can get rid of that one. Yeah, so we should get rid of tab. It's not a question of which one is better. It's which one can we get rid of. The tab character is an anachronism that should have died with the typewriter. All right, we finally settled that. OK, we have carriage return and line feed. Again, these are because of the way that the teleprinters worked. Carriage return would move the print head back to the margin, and line feed would roll the paper up one line. And they liked having the two codes because the carriage return function was kind of slow, because you have to move the thing down. And having the line feed happen just after it gave it a little bit more time to have that. Because if you then have to print another character before the carriage return gets back, you're going to be printing ghost characters in the middle of the page, and that looks stupid. So we don't care about that anymore. That's not how printers work now. But we still have these two codes, and there's still an argument about which one should you use. People who think about this in terms of user experience will usually say it should be the carriage return, because the enter key used to say return, and so that's how users think of this. The hardware-oriented people say line feed is really the way printers want to work. They want to advance to the next thing. And so, how do you decide which one to do? Well, there was a committee in the early days of the internet who tried to decide which one should we use. And they couldn't decide, so they came up with the mutually disagreeable compromise, which is we'll use both of them, which doesn't make any sense. That using both of them went out with mechanical teletypes, but we're still doing that. If you look at the internet standards, look at HTTP, it still says you have to use both of them. It doesn't, both at the same time. It just doesn't make any sense. We also have form feed, which told the printer to eject the current page and put the next page into the printer so you could start printing. And a companion vertical tab, which is the vertical version of the horizontal tab. But again, they didn't specify any way of setting a vertical tab stop, so today it doesn't make any sense. JavaScript still lets you say \v representing this. It doesn't mean anything. It's pointless. There were 4 device codes in ASCII so that you can control devices, and generally that meant controlling the paper tape reader and the paper tape punch. So your teletype might have a paper tape reader on it, and if the computer wants to start reading it, it can turn the reader on, and then it'll start automatically sending characters to the computer. And if the computer starts getting overwhelmed, oh, there's too much input, you can then tell it to stop. And the computer could also turn on the punch so you can start punching your paper tape. Those codes are still in ASCII. Then there are codes for dealing with protocols, because they imagine that instead of just sending streams, that we might actually be sending higher level stuff. And so this was really new stuff that they were kind of inventing. So they imagined that we'd have protocols in which we'll have a start of header and a start of text code and an end of text and an end of block. And we'll use those to make packets. Packets were still a really new idea. And then in support of that, we have ACK, the acknowledge code. So if you successfully read a packet, you'll send it back ACK. And if for some reason you couldn't read the whole packet, you'll send back NACK. And there's also the synchronous idle. They anticipated a synchronous mode in which, well, in asynchronous mode, there's a start bit and a stop bit on each character. And that's, so you've got an empty stream, and then you see a start bit, and you go, oh, wake up, there's a character. And you keep getting bits until you get the stop, and then you can go back to sleep. But there's also a synchronous mode in which the characters go one after another, no start bit, no stop bit, then the problem is how do you know where the character boundaries are, because it's just ones and zeros. And so they have a synchronous idle. So when there's nothing being sent, you send this code. And on the other side, they'll be looking for a pattern of those zeros and ones. When they see them, they go, ah, that's a character. And then they can deal with the rest of it. So a packet might look like this. You might have a start of text, and then the body of the message, and then the end of text. Or you could put a header on it. The header might contain an address or some other information which helps you to deal with the packet. And using the end of text block, you could have really long things, and you could get an ACK after each one, because it might be too dangerous to try to send something really long, because it's guaranteed you're going to get an ACK. So if you send it in smaller chunks, then you might get stuff through. There were two end codes. One was end of transmission. So at the end of a session, you go Control D, and that's the end. Then we can hang up, and we're finished. And there was also end of medium. This is something you might put on a tape. So you write a tape, and at the end, you'll write an end of medium code, and that means that's the end of the tape. Then there are a couple of oops codes. There's the substitute code. That means that if you have a character and you don't know what it is, you send the substitute code instead. You know, again, today, the way we think about data communications, that doesn't make any sense. How can you not know what a character is and still want to send it? But you could do that. Also, there's a cancel code. If something is coming, or if you're sending something and you decide, oh, never mind, I'm not going to send the rest of it, you can just send the cancel code, and you're done. There's escape. Escape was not what we use it for now. Escape was for extending the character set. They anticipated that the 128 characters in ASCII might not be enough. So escape would allow some way of extending the character set. So when you see the escape code, that means the stuff that comes after it is going to be interpreted differently. One interpretation that was popular for a while was add an 8th bit to the character. So that would get you up into the Latin 1 set. So there was an escape key on the teletypes for that purpose. But very quickly, people realized, we're in a program, and we want to make the program stop. How do we do that? They go, well, I've got this escape key. Let's hook that up. And we're still using it, right? Escape gets us out of a mode or cancels a dialog or something like that. It was never intended for that. It was intended for enhancing the ASCII set. We have data link escape, which does a similar thing. Sometimes it's used for making a control code literal. So if you've got some binary data and you want to be sending an end of transmission mark, but you don't want to hang up, you want it to be treated as data, you might put a DLE in front of it. But it could also be used to introduce new control codes, because they were concerned that 32 control codes were not enough. They thought they might want a lot more. Then I told you about the shift codes for uppercase and lowercase. They decided not to use them for that, but they still put them in the code. And so you could shift out, meaning you could shift into another character set and then shift back into ASCII. Another way of growing the code. They provided information separators. So there's the file separator, the group separator, the record separator, and the unit separator. So they did not intend for, or I've heard people say that tab separated data is the way ASCII intended us to format data. And it's not. This is how ASCII intended us to format data. You have files made up of records, made up of groups, made up of units of data. Unfortunately, this isn't really how data ended up. That sometimes you have records that really want to contain other records. So this doesn't work. So I should have told them about JSON, right? Because that's what they really should have been doing. But I didn't. And my excuse is that I was 8 at the time. And I was doing other things. I was just too busy. Yeah, so that's the ASCII set. So again, they did not intend this to be a computer character set. This is just something that computers would use to communicate with each other. But a number of manufacturers thought, well, let's just try to use this as is, because then we don't have to translate from our set into their set. For one very common use was something that I called half ASCII, where you just take 64 characters of it, you cut out the control codes and the lowercase, you just subtract 32 from everything, and that gets you a nice little 6-bit character set. And there are a number of manufacturers that were doing stuff like this. It all changed with the microprocessors, but we'll get to that in a bit. So the next step forward is Unicode. Unicode starts in 1991. Some very, very smart people from Xerox and Apple and other places who have been really struggling trying to make products that worked all over the world, and realized we need to figure out a way to unify the character set so we can just have one product that goes everywhere. And so their goal was to make a character set that would serve all of the living languages in the world in 16 bits. And they came really close to pulling it off. But in order to do that, they had to do something called Han unification, which meant observing that Chinese was the root also of Korean writing and Japanese writing. And taking all three of those languages, putting them into one character set, it's too big, doesn't fit in 16-bit character sets. But if you look at how common those languages still are, at least in their orthography, then we can squeeze it down into 16 bits. And they tried really hard to do that. Unfortunately, they really pissed off the Japanese. They were not happy about the way that happened. So that brings us 5 years later to Unicode II. And Unicode II now has a much more expansive mission. They have grown the character set to 21 bits, and they now want to encode all languages, even dead languages. So Egyptian hieroglyphics become part of Unicode, which is something I like a lot. So I like that. Unfortunately, in 2010, we get Unicode 6 and emojis. For a while, there was a hope that someday we could finish Unicode, right? That we'll find all of the languages that have ever existed, and we'll write them all down, and we'll give all the characters codes, and we'll be done. Unicode will never be done. There's no way we're ever going to run out of emojis. So ASCII lives on in Unicode. The first 128 characters of the Unicode set are the ASCII set. Even though ASCII was not intended to be a character set and Unicode was intended to be a character set in computers, ASCII is in there, including the 32 control codes, which you now know are mostly meaningless and completely ridiculous, right? They don't serve us anymore. And the way this stuff works is really important. For example, in the C language, we use the null character to represent the end of string, which is not what ASCII said, but that's what C says, which means that C would have broken on any of the earlier 6-bit character sets because they did not have a null code. They all used 0 for a real code. So ASCII changed the way we think about programming of letters and words. But there was an even bigger influence than that. Under the influence of 6-bit character sets, there were lots of different hardware architectures with lots of different word sizes, but they all seem to have a factor of 3 in them. So I saw and worked on machines that had 12-bit characters, 18-bit characters, 12-bit words, 18-bit words, 24-bit words, 36-bit words, 48-bit words, 60-bit words. The thing all of these machines had in common was 6-bit characters. And the reason that worked was because that's what the character sets were. And so you could pack some number of characters into a word, and it all fit. And it was really good. And these were great machines. And then it all changed. So 7-bit ASCII caused the ascendance of computer architecture based on 8. So IBM took ASCII and weirdly mutated it. They combined it with their terrible BCDIC code and came up with something, a really awful thing called IBCDIC, and used that as the character set for the 360 series. So that system is based on 8, 16, 32. And all of our machines pretty much since then are based on that. The big change, I think, happened because of Intel. So Intel built a machine called the 8008, which was, the design was brought to them by a company in San Antonio called DataPoint. They made intelligent terminals, and they were making them out of discrete logic, and they were difficult to build. And they came up with a design for a simple CPU, which would have greatly simplified their terminals. And they asked Intel if they would build that chip for them, which they did. So the initial design of that chip was an 8-bit machine. And the reason it was 8-bit was so that it could process ASCII. That was the intended purpose of the 8008. But that 8008 grows into the 8080 and the 8086 and the Pentium and all the crap that comes after. And so it's all 64 bits now. So if the ASCII committee had successfully completed as a 6-bit character set, 36-bit architecture would have survived. And so I think the first microprocessors would have been 12-bit machines, not 8-bit machines. And that would have completely changed the evolution of stuff. That the next step up would have been 24. And so a lot of the memory limitation issues that we felt on PCs, we could have avoided those for years and then taken the next step up to 32. And today, we would be running in 72-bit architecture, which I think would be brilliant. And it would have completely changed the way we do internationalization. Europe would have moved immediately to 12-bit character sets because 6 didn't work, in exactly the same way that Asia moved immediately to 16-bit character sets because 8 didn't work. And by doing that, we would have avoided all of those internationalization problems. And then ultimately, the world would adopt an 18-bit character set, which would be the Unicode set, which would serve everybody. And 72-bit CPUs would be the standard today. So that's the end. So I'm really looking forward to some excellent questions, which will help me figure out what the wow finish is to this thing. So any questions?
Do you see a trend in us observing mistakes like this, like the one you just mentioned, moving where we could have been 12 bits instead of 8? Are we learning from our mistakes in this field?
Are we learning from our mistakes in this field? No. No, we generally don't do that. We will adopt something because it seemed like a good idea at the time, and we tend to never revisit it again. And so, you know, as you look down into the history of what we've done and why choices were made, and then see where they ended up, you know, it just, you know, if we had known where it was going to go, we wouldn't have done that. But somehow we're still here where we are, and we don't recognize that we're still doing that. And that's just the way we do things. Yeah?
So given that so many of the problems that we've had have come from people not anticipating that things may change going forward, do you personally see a path that you would prefer us following to anticipate that what we're looking at right now as our current framework may not be what we have to deal with going forward?
Yeah, what's the path going forward? That's a really hard problem. I mean, I commend the ASCII committee for doing as well as they did. I mean, they got a lot of stuff right. They were very thoughtful in the way that they approached the problem, and they did the best they could. Where it went wrong, I think, was not in the ASCII committee, it was after. Again, they didn't intend for it to be a computer character set. They intended it to be a transmission code. But there were people, particularly in the 8-bit world, who wanted to save the cost of a character translation table. They wanted to save 128 bytes. And if we make that our character set, we save 128 bytes. And at the time, that seemed like a really good trade-off. But it was only a really good trade-off for a few years. Eventually, Moore's law changes the economics of memory conservation, and then it becomes a really bad idea. But again, once we lock something into a standard or a standard practice, it's virtually impossible to roll it back. Yeah?
So it sounds like we've made some mistakes, but you can only go forward. So is there a way to go forward in a more malleable and corrective direction? If we do make mistakes, it's easier to sort of pull back on ourselves and fix things when we need to.
Yeah, that's a really good question. So you would think so. That's a really good, thoughtful question. I'm afraid I don't have an adequate answer for it. But thank you for that question. Yeah.
Are there any strides to come up with other standards other than Unicode that don't take into account the ASCII?
Yeah, so are there any alternatives to Unicode being considered? I don't think so. I think Unicode is likely to be the last character set. That it's just going to be the way it is. And there are some things about Unicode that I think are extremely commendable, that they've done some brilliant stuff. And there's other stuff in Unicode where you go, this is awful. Like I showed you that substitution code in ASCII, the one that says the letter you're looking for, it's not here, or the code you're looking for, it's not here. Not only is that code now in Unicode, Unicode added another one. So Unicode has its own substitution code saying, well, it's not here, which we need 0 of those codes, right? And we've got 2 of those codes. One of the things that was liberating about ASCII was because they've got so many characters, they didn't have to be nearly as cautious as ASCII was. ASCII, when they were picking the characters to go in that set, they made really, really hard choices. If we put that one in, we can't put that one in. They didn't put the arrow in because they just couldn't make it fit, it was actually in there for a while, and then it got taken out and replaced, I think, with the underbar. This stuff's tough. I could anticipate, I could think of one thing that might propel the world to consider doing a new character set, and that would be something that would try to solve the sorting problem. So Unicode sorts correctly for virtually no languages, right? Well, or at least for the languages using the Latin set, that none of the languages sort correctly. We could try to, and there is no ordering of the letters that will sort correctly for all languages, but we could come up with a sorting which would work for most languages. So we could design a character set in which we have A followed by A accent, followed by A umlaut, and so on. We'll just batch them all up. After I comes IJ, and then J, and then K, and so on. We'll just try to take as many of the European characters as we can and put them into one linear sequence. And maybe that becomes a good enough idea that we can say, this becomes the basis of a new character set. I can't imagine anything else. I think that would be a problem that would be worth solving. And that might get us a new character set, but I'm really doubtful. I don't think we could pull it off. There is so much inertia behind Unicode now, I think it's going to be the end. Yeah?
Is there any way to work in 3 dimensions with character sets?
Is there any way to work in 3 dimensions in character
Yeah, well,
sets?
it seems like we're going left to right, top to bottom. Why not go backwards?
Well, you could stack them up, and that's essentially what Unicode does. So in Unicode, you've got, it stacks them in a couple of dimensions. One is you've got planes. So you've got the basic plane, and then you've got 16 additional planes, which are all in the same 16-bit set. And within the 16-bit set, you could see that is broken into stacks of 8-bit sets. So that's a 3-dimensional character set. All right, yeah?
I guess the question that I had, so I guess in your opinion, is there any way you could estimate like the economic cost from having all these inefficiencies and like things that we're dealing with that are not necessary?
Yeah, that's the problem, because there are definitely costs, but all of those costs have already been accepted. So in changing to something better, it's really hard because it's obvious that there are going to be new costs in moving to the better system, and it may not be immediately apparent what the benefits are. Whereas we don't properly account for the costs in the old system. So the new system is going to be at a huge disadvantage. Yeah?
Could there be advantages in compression by altering the current character set?
Could there be advantages to compression by altering the character set? Maybe, although some of our compression codes are smart codes that learn and are adaptive, so they seem to be doing pretty well. I don't think we could get much improvement by changing the underlying character set. Yeah?
So what are some of the advantages afforded by having a 72-bit architecture over a 64-bit architecture?
It's more bits.
I mean, I guess you were arguing that your memory barriers that you sort of had in the history would have been further out.
Yeah, so the memory addressing problem we passed, 64 bits looks like we're going to be good for a long, long time with that. And 64-bit is, well, so in JavaScript, we get essentially 53 bits, at least in our integers. And that's quite a lot, particularly when you compare it to the 32-bit architectures. And much of JavaScript, unfortunately, is still 32 bits. And there's been some pressure to try to get JavaScript to add a 64-bit thing, which I'm very opposed to. That if you want extended arithmetic, you can write a simple function in JavaScript that gets you extended precision, so we don't really need to change the language fundamentally. And if you have 2 number types, and if they ever come in contact with each other, you're guaranteed to have errors, right? Because values are not, yeah, that kind of stuff. So I'm very unhappy with the floating point system we have in JavaScript. It's horrible. But I can't see that we're going to replace it because, again, we've accepted all the costs of a floating point system that works really badly. And so we're not going to be able to overlook the costs of moving to something that's going to add money correctly, even though that I think is much more important. I think DEX64 would be great, and I highly recommend that DEX64 be the only number type in the next language. But I have no hope that it will ever get into JavaScript. JavaScript is, or as Brendan Ike used to say, that ship has sunk. Yeah.
Just one more question. So I'm a little familiar with the topic, but the idea of quantum computing is that now you're not limited with ones and zeros.
Yeah.
So the whole idea of having 18 bits, you would need a lot less bits if you do that. I guess, do you know anything about that? Or?
Quantum computing is a completely different thing. So you've got these quantum bits which can be in multiple states simultaneously. And it's presumed that that leads to the solution of problems which cannot be solved in linear time on conventional hardware. But they don't act like bits. So there's not a correspondence to bits. They're different stuff. So even if we do get quantum computing, I think it will be used in very specific applications, things where you get the benefit of the undecidability in order to solve very hard problems. One of the most popular expected applications seems to be breaking of cryptographic systems, so which will certainly be problematic. But it doesn't appear that it's going to be a platform for general purpose computing. So I think we'll still have bits for a long, long time. Now, a more interesting breakthrough might be trying to figure out the neural stuff. That we still haven't figured out how this stuff works yet, but we know really well now that it works really differently than digital systems. So it may be that eventually we'll figure out how to make neurons and stuff like that, and that will work on a completely different principle. And who knows what we'll do with that. Anybody else? OK, so I think we're done. Thank you very much.
Thank you.
All right. Thank you all for coming. Thank you to Douglas for doing an excellent presentation. Thank you to LearningFuze and Bill. Sorry I didn't say that at the beginning, but really owe LearningFuze a lot for putting together this event and just making it like awesome. So yeah, after this, it's already on YouTube now, the video. We got a lot of feedback on the live stream side of things saying that they could hear the audio and video pretty well. So yes, yay, thank you to everybody watching on the live stream. It's awesome. Yeah, I think I kind of had said to Douglas, if somebody had asked questions, to throw out a few t-shirts. I think what we'll do is, like we'll do it like last time actually. I'm just going to throw these out and just catch. Okay. And I have some books for you guys. Like, I have books, I have pens, I have some cell phone case stuff for you guys here. No, I don't want to hit anybody in the eye with this. So feel free to grab something from up here. Don't all rush at once. Like, respect your neighbor. That said, thank you again. I mean, like, this is amazing. Thank you guys for coming out. Stay tuned for more meetups. Lots to come. Does everybody know what our JavaScriptLA YouTube channel is? Shout it out if you know.
JavaScriptLA.
That's right. YouTube.com/JavaScriptLA. A t-shirt. We also have Instagram. It's called JavaScript Ninja. That's the only one that's different from everything else. Facebook.com/JavaScriptLA. YouTube. They're all the same. So I hope to see you guys post comments, especially if you had questions tonight and you didn't feel like you could ask it at that moment. You want to review the video. Maybe you have questions, you can send it, and we'll try to send it to Douglas. OK. Does anybody have questions for me or Douglas at this point? Yes?
Not really a question. I think you had a typo on one of your slides, Douglas, in the spacing. I think the binary code for the space was incorrect.
I'm sorry, on which side?
On the spacing, where you put the binary code on the left, I think you had 16 instead of 32 for the space. I mean, not a big deal, just a typo for you.
Give me a better picture so I can find it.
Right at the beginning where you had space and tab.
Oh, yeah?
I think the binary code for space was wrong. I might be wrong, but I think the binary code for space was wrong.
Oh, great, great. Thank you very much.
All right. OK. With that said, come by here. I'll give you something. If you want to talk to Douglas, be sure to have questions. Line up, be respectful, that sort of thing. And thank you all for coming.